to find the determinant in a more efficient manner. But you should be able to now find the determinant of any size matrix, given the fact that the cofactor expansion along any row or any column is the way of doing so. So if you do a 5 by 5 matrix, the idea is that you go along one of the rows, one of the columns, and you perform the cofactor expansion, which means you take a smaller submatrix, which would be a 4 by 4 matrix, and find the determinant of that until you get to a smaller enough determinant that you can compute yourself, and then you go your way back out. So there's not much of a difference after you understand the general procedure, but there is a technique of rearranging the determinant so that you can find a determinant much simpler than having to do the cofactor expansion. So I do want to show you that. So I'm not going to show you how to find the determinant of a 5 by 5 matrix because we already have discussed how to find the determinant of any matrix, but there are quicker ways. Yeah, actually. So I know I promised you guys a review sheet for today. I don't have it for this session, but we all going to review. But I will provide it by either tomorrow or Friday, and I will have the review session that I have promised you guys on Monday, and I'll send you the information on as to what time on Monday, and most likely it'll be at night, Monday night, on Zoom on the same thing. Yes, so let's continue with the properties of determinants. So at the end of the class, right, we started talking about the different properties of determinants. So we know that the determinant of the identity matrix is 1. It's a diagonal matrix. So when you find the determinant of a diagonal matrix or of a upper or lower triangular matrix, you multiply by the entries along the main diagonal. So an identity matrix have entries that are full of 1, so the determinant is going to be 1. And then we notice that when we apply the determinants to elementary matrices, and there's 3 kinds, right? There's ones that swap the rows, there's ones that multiply a row by a scalar, and there's ones that multiply a multiple of a row to another row. And we notice that if we just swap the rows, if we swap the rows of the identity matrix, the determinant of that matrix that represents the swapping of rows, you're really multiplying by negative 1s. And when you multiply a matrix with the elementary matrix that has when you multiply a particular row by a scalar, then the determinant of that matrix, elementary matrix, is just the scalar, that whatever that scalar is, because of the way that the elementary matrix is a diagonal matrix, and the determinant would be just the product of the main diagonals, which would just result in C. And the nice thing is when you find the determinant of an elementary matrix that represents adding a multiple of a row to another row, it's actually just the determinant is just 1. So, so what would determinant of a cubed be? That's a very good question. And that results right into the next column, which is the general properties of determinant. So we know the determinant of the identity is 1. The determinant of A transpose is equal to the determinant of its original matrix. And you can also accept that because rows and columns, it doesn't matter what row or column you perform cofactor expansion upon, the determinant results in the same thing. So it makes sense that the determinant of the transpose of a matrix is equal to the determinant of itself. The next property which we saw in the previous example in our most recent lecture is that if you have a column or one row of zeros, then the determinant of that matrix would be 0, because if you perform cofactor expansion along that row or column of zeros, you get a whole bunch of zeros. That makes sense as well. Now, the last 2 properties are very important, and in a sense, they're almost like they're almost symbiotic here. So if you understand the fourth and the fifth, well, if you understand the fifth property, then you would know how to find a determinant of a cubed. So the idea is that the determinant of a times b is equal to the determinant of a times the determinant of b. Upon this property, so for example, given your question, Tassif, if you want to find the determinant of a cubed, well, remember what a cubed is. It's the determinant of a times a times a. Now, under this property, I can find the determinant of a product of matrices as as the product of the determinants of each of the matrices. So this would be the same thing as saying the determinant of A multiplied by the determinant of A multiplied by the determinant of A, which results in the determinant of A cubed. So that would be the result. So the determinant of A cubed would be the same thing as finding the determinant of A, and whatever that number is, cube it. Okay. And now, based upon this, you can actually show why the determinant of -1, the determinant of the inverse of a matrix, is equal to 1 over the determinant of that matrix. So let me show property 4. Show property 4. Property 4. So we know that if you have A times A inverse, you get the identity. And then if we apply the determinant of A times A inverse, we get the determinant of I. But the determinant of I, the identity matrix, is 1. And applying property 5, we know that the determinant of A times the determinant of A inverse is possible. And when we divide out the determinant of A on both sides, we get that the determinant of A inverse is equal to 1 over the determinant of A. So this property here is an extremely important one. The determinant of the product is equal to the determinant of the product of their determinants. So that's a really nice property of determinants. Okay. So based upon these properties, I want to show you so look at this example. Suppose I have a matrix, right? A, B, C, D, E, F, and G, H, I. So these are the entries, right? Oh, yeah. So you're asking very good questions, Tassif. So hold on 1 second with that. I'll show you how that would look like. But let's go on to this first. Determinant of A. Let's suppose. So suppose is equal to -6. Okay. So find the following. What would the determinant of A, B, C, D, E, F, and G, H, I be? What do you notice about this determinant matrix that we want to find, the determinant of this matrix that I want to find? compared to this? They have the same letters, but what's the difference here?
First and last rows switched.
Yes, so we swapped rows. We swapped row 1 and row 3. Now, this is equivalent to saying I want to find a determinant of an elementary matrix being applied to A where E swaps rows 1 and 3. And applying the property number 5 of the product of two matrices, this would equal what? The determinant of E multiplied by the determinant of A, correct? But what is this determinant of an elementary matrix who swaps rows? What do we know about it from here? Well, if we have an elementary matrix that swaps rows, the determinant of that matrix is -1. So this becomes what? -1 multiplied by -6, which equals 6. So again, swapping the rows of a matrix is only going to affect the sign of the determinant. So if I were to swap this again, for example, if I swap 1 and 3, and then I swap this matrix again with 2 and 3, and switch that, then I'm going to multiply the determinant by -1 again, which will give me back -6. So depending upon how many times I swap my rows, it's going to affect the number of times I'm multiplying by -1. Okay, so if I swapped it one more time, then this 6 will become now -6. If I swap it again, this would be -6, +6, so on and so forth. Does everybody understand that? So just swapping the rows, I multiply by -1 for every iteration of swapping. Okay. What about this one? 3A, 3B, 3C, -D, -E, -F, 4G, 4H, and 4I. Now, what would be this determinant? So compare with the original matrix. ABC, the first row, has a 3 in it, correct? The second row has a negative for each, has a -1 for each entry in the second row, and then the last row has a 4 in each entry being multiplied. So what did I really apply here? What elementary matrices or what elementary row operation did I apply?
Scalar multiplication.
Right. And how many of them? How many scalar multiplications have I done?
3 of them.
3. So then I can consider this as what? The determinant, let's call this E3, E2, E1 multiplied by A. Now what does E1 represent? Scalar multiple, right? Multiply row 1 by 3. This is multiply row 2 by -1, and then multiply this, multiply row 3 by 4. So this equals what? What does this equal? This equals the product of the determinants. Determinant of E3, determinant of E2, determinant of E1, determinant of A. So what's the determinant of E3? Well, if I multiply by a row by a scalar multiple, it equals what? It equals that scalar multiple, right? So this would equal a 3. How about E2? E2 multiplied by -1, so it's -1 multiplied by E1, which represents multiplying row 1 by 3, which will give me a 3. Oh, pardon me, this should be a 4. And then the determinant of A is 6. So then when you multiply it all out, what do you get? Negative 4 times 3 is negative 12. Negative 12 times 6 is negative 72. Does everyone follow this? Does everyone see how the elementary matrices, how they're embedded in this kind of problem with multiplying rows by scalar multiples? Is that clear? Sam?
Wouldn't the 6 be a -6 because we're taking from the first
Oh,
matrix?
you're right. You're right. You're right. You're right. You're right. Pardon me. Yes. Yes, this should be positive. Thank you. Thank you. I was just looking at the 6 here. You're right. It is -6. Thank you, guys. That's right. So it should be a positive 72, not negative. That would be wrong. Okay, so now to answer Tofsif's question, what happens? It says, what happens if you take the determinant of twice A, right? And we can use this problem right now. So I'm gonna make that a question here. What's the determinant of twice A? 2 times A. What does that mean? 2 times A. That's the first question you should ask. Do you know what this would mean? Two times the matrix. So what does that mean? When you multiply a matrix by a scalar, what are you doing to every entry?
You're applying it to every entry.
Right. So then if you use the same A here, right? If you were to use the same A here, you would use what? This is 2A, 2B, 2C. This would be 2D, 2E, 2F, 2G, 2H, 2I. So guess what's going to happen? I am multiplying, right? What am I doing? Determinant of E3 times E2 times E1. I am multiplying my matrix A with 3 elementary matrices that multiply the first row by 2, the next row by 2, and the last row by 2. Which means I'm taking the determinant of each one individually. But I already should know what's going to happen next. Each one of these matrices is equal to 2. So what do you get? You get A times -6, which is -48. So do you see what happens? If I have a matrix and I multiply one row by a scalar, then the determinant is multiplied by that scalar that I multiply the row with. If every row is multiplied by that same scalar, then I'm multiplying that number, that scalar, I'm multiplying that number 3 times in this case to the determinant. So then there's another property. So these properties continue. So an additional property, you call this number 6. So if A is n by n, then, and A is invertible, we were assuming A is invertible. Yeah. And A is invertible, then the determinant of K times A is equal to K to the n times the determinant of A. So if you have an n by n matrix and it's invertible matrix, the determinant of a scalar multiple multiplied by a scalar multiple k multiplied by the matrix A, well, the result is you take k and you raise it to the nth power because it represents that you're multiplying every row of A by k n times, right? And so that's k to the n times the determinant of A, which is what we got here, 2 cubed. Do you see that? So that's the general property here. So does that answer your question now? Great, great. So if this was a 3, for example, it would be 3 cubed. If this was a 10, it would be 10 cubed, and so on. But very good question. Okay. Now there's another property that I'm going to discuss using this little example here. So this is the fourth one. And this is also very important, guys, very important. So for example, something like this, A, B, C, 2D, 2E, 2F, and G plus 3A, H plus 3B, and I plus 3C. I want to find what this is. So what do you notice? First row, untouched. Second row, pardon me, scalar multiple of 2. So I'm going to be multiplying by 2. So now eventually I'm not going to be doing this every single time, right? Like the whole breaking it down this way. But now we can go a little quicker. And then the last row, what's the last row?
You're adding a scalar multiple of another row to that row.
Right. I'm adding a scalar multiple of another row, of one row to another row. And then what do we know about the determinant of those matrices? They're always equal to what? 1. What does that mean? That means if I add a scalar multiple of one row to another, I don't change the determinant of the matrix. That's really important. So this becomes, if just to do one more time, this illustration, I'm really taking 2 elementary matrices and applying it to the matrix A. One of them is multiply row 2 by 2. And then the last one is add a multiple, add 3 times row 1 to row 3. So then we know the determinant of E2, this is 1. The determinant of E1 is 2. Determinant of A is -6. So we would have something like 1 multiplied by 2 multiplied by -6. So the determinant would be -12. So note, adding a scalar multiple of one row to another leaves the determinant of the matrix unchanged. So that doesn't change it. That's really important and that's really helpful, useful. And this is the technique that we're going to use. This is the reasoning we're going to be using to find better ways of finding determinants of larger matrices, such as a 5 by 5 one. So there's two things that I want to touch upon with this. Is one thing is the invertibility of matrices and how that's related to determinants. That's one thing. And the other thing is this scalar stuff. So actually, I want to go with this. So we can use our knowledge of elementary matrices and properties of determinants to compute determinants more efficiently. And the idea, and I remember back in the I don't know which lecture it was. I remember someone asked, maybe you can remember, someone asked, what is the point then of learning about row echelon form if we only use, or it appeared to be that we only use row reduced echelon form, right? We cared about the row reduced echelon form every single time when we applied Gauss-Jordan elimination. And so someone asked, I remember someone asked, what does it matter if we, why does the row echelon form matter? Well, actually, this is one point in time where I can remember and say, this is when it does matter. And actually, it's more important in a way than the row reduced echelon form. And why is that? Because once we're able to use these ideas of elementary row operations, elementary matrices, and these properties of determinants, then, for example, if I want to find the determinant of something like this, right? -3, 0, -6, 7, 1, and 9, -2, 5. What do we normally do for this? We can do two things. We can use cofactor expansion along any row, any column you choose. There's a 0 here, so you would probably use either the first row or the third column to find it, right? Or you can use a trick that we learned, right, when we place these first row, the first row here, and the first column and the second column, and then we use those little arrows diagonally, and we multiply those numbers. We can do that as well. So there's two ways to do this problem, and I'm going to show you a third way, and it's related to row reduced echelon form. And so recall row echelon form, and this row echelon form is actually a triangular matrix. So really what we're doing is we're taking matrices and making them triangular. How do you go from this matrix into row echelon form? What are you applying every time?
Elementary matrices.
Right. And what do you know? There's only 3 kinds. So what happens for every single row operation that's associated with the elementary matrix? You either, when you swap the rows, you take that negative sign, right? You multiply a row by a certain scalar. So then you multiply the determinant by that scalar, or you multiply by a multiple of a row to another row, which leaves the matrix unchanged. And then once you have that matrix in its row reduced echelon, and not row reduced, in row echelon form, it's a triangular matrix. And how do you find the determinant of a triangular matrix, whether it be upper or lower? What's the only thing you have to do?
The diagonal, multiply it.
Right.
Yeah.
So we avoid the whole cofactor expansion, which is multiple determinants being found at once. And this is helpful for not necessarily for this one because we can do the trick for the 3x3, but let's say we do a 4x4 or 5x5, and we can find ways to put that in the upper triangular form, which is the row echelon form, and just multiply the diagonals entries, and keeping in mind that we're switching or whatever operations we're doing here. So let's do that for this, and then we'll look at a bigger example, and then we'll see how it's useful. So what's the first thing I would do here to put this in row echelon form?
Multiply R1 by a third.
Right, so I could do that, right? So this is a 1/3 R1 to R1. So then what does that do? So this becomes what? 1, -2, 3, -2, 7, -2, 0, 1, 5. But what did I just apply? I applied a row operation, right? So this 1/3, how does that affect the determinant of this matrix?
Multiplied it by that scalar.
Right. So this becomes 1/3 has to pop out. Because that's what I'm doing. I'm applying this elementary row operation, which is associated with the elementary matrix, where it has that 1/3 in the first entry, and the determinant of that matrix is just that scalar. So this is what I have. I have 1/3 multiplied by this guy. Now I want to make this into this, right? -2 in row 1. Say that again.
I have a question. How come the -6 didn't change when we took out the
Oh,
1/3?
I think that's what Interpret says. Thank you, Interpret. Yes. Yeah, it should be a -2. That's right. So you divide everything by 3, so you get -2. So now what? Again, all I want to do is put this in row reduce and row echelon form. I'm not trying to go all the way to row reduce echelon form. So I just want to have the zeros here. That's all I want to do. I want to have 0, 0, multiply the diagonals, done. So then I want to get rid of this -2, right? So what do I have to do here? 2 row 1 plus row 2 to row 2. What happens when you do this step? What do you do when you add a multiple of a row to another row? The determinant, we just said it here, right? Adding a scalar multiple of one row to another leaves the determinant of the matrix unchanged. So this very process right here, even though my matrix looks much different, it's going to look like 1, -2, 3. I'm going to have 0 here, first column, right? Then I'm going to, I'm just multiplying by 2, so it's 4. This becomes 3. And then this becomes what? Was it 2, 6 is 4, right? And this becomes 1, 5. In doing so, in applying this process, in this step, I leave the determinant alone. So I don't do anything. I just change the way it looks. So I'm almost upper triangular. I'm almost row echelon form. And I think now, Tassif, it would be a good idea to switch rows 1 and 2. So I'm going to swap row 2, 3 and 2 and 3. And in doing so, what happens when I swap the rows? What appears in the product now? So when I swap the rows, right, I'm multiplying by a matrix that swaps the rows. That determinant of that matrix that swaps rows is equal to -1. So there's going to be a -1 that pops out in the matrix, in the determinant. So there's going to be a -3rd instead. And then I'm going to have 1, -2, 3, 0, 1, 5, 0, 3, 4. The reason why I did that was because I don't want to, I don't have to divide this by 3 anymore to make this into a 1 so I can get rid of this. I can just straight up from here now say what? I want to take negative 3R2 and add that. Should maybe put this in a different color. Negative 3R2 plus R3 goes into R3. So this becomes negative 1/3 multiplied by 1, negative 2, 3, 0, 1, 5, 0, 0, and then negative 3, this is negative 15 plus 4, it becomes what? Negative 11. And now look what we have. This is row echelon form. Upper triangular matrix. Once we have an upper triangular matrix, to find the determinant of upper triangular, just multiply the diagonals. And what do we get? We get 11/3. Does everybody see what I did? For every step, I'm applying a elementary row operation. Every row operation affects the determinant either by multiplying by 1 when you, negative 1 when you swap rows, leaving the determinant alone if you add a multiple of one row to another, and if you just multiply straight up a row by a scalar, you're multiplying the determinant by the scalar that you multiplied by. And so these are the 3 operations that I applied, and I got the last matrix here expression is in upper triangular form because I put it in row echelon form, and I just have to multiply the entries, diagonal entries for that. And overall, I get 11/3. Does that make sense? So now let's look at a bigger one. So if I want to look like a 5 by 5, you're getting every question hopefully being answered, Tassif. So 1, 3, 1, 5, 3. This is negative 2, negative 7. But don't worry, we're not going to be doing too crazy of a matrix. We're going to have a pretty sparse. So that's another word that people use a lot for matrices that have a lot of zeros. The word is sparse. So a sparse matrix has a lot of zeros in them. Sorry, this should be 2, 1, 1. And this is 0, 0, 0, 1, 1. So if I want to find a matrix, the determinant of such a matrix here, right? I could do cofactor expansion because that's always a viable option. But then the moment you do this, for example, if I wanted to go along this row, right, what happens? I have to find the matrix, the determinant of this smaller matrix. And then if I do like this, then I have to find another determinant of a smaller matrix. And the great thing about that is you have a lot of zeros in them. So you can just continue your way on. Or you can just write this because this is almost in what? This is almost in row echelon form. It's almost a triangular matrix. So all I have to do is get rid of this negative 2, get rid of this 2, and get rid of this 1. So how do I get rid of the negative 2 up here? What do I apply?
You could do 2R1 and add it to R2.
Right. And when I do that, what happens to the determinant?
Stays unchanged.
Stays unchanged. I don't change it. All I'm changing is the matrix, right? So this becomes 0. This becomes 0, 0, 0. And then when I multiply by 2, I get 6 plus negative 7. I get negative 1 on the diagonal here. And I get 2 times, I get 2, 10, I get 6, and then 6, I get 8. But if you notice, well, for now it does matter. So this is 0, 0, 0. This is 1, 0, 1, 2, 1, 1, 0, 1, 1. Oh, interpret, you have a parrot. That's that's pretty cool. No problem. Yeah, that's hopefully your parrot is enjoying seeing all these numbers and hearing me speak. Okay, so we got rid of that. So the determinant is unchanged. And now I just got to get rid of this 2 and this 1. So how do I get rid of this 2 here? What does your parrot say in Dupree? I'm going to get rid of this 2. Pretty simple, right? I get negative 2 R3 and added to R4 into R4. But of course, applying this step here doesn't affect my determinant, which is nice. So I get 1, 3, 1, 5, 3, 0, negative 1, 2, 6, 8, 0, 0, 1, 0, 1, 0, 0, 0. Then this becomes 1 still, and this negative 2 added to 1 becomes negative 1, and I get 0, 0, 0, 1, 1. Oh, wow. So look what we have so far. We got negative 1. We had the pivots. Well, yeah. And then lastly, I want to get rid of this 1 here. So what do? Negative R4 plus R5 into R5. Again, this doesn't affect my determinant whatsoever. So I get 1, 3, negative 1, 0, 0, 0, 1, 2, 1, 0, 0, 5, 6, 0, 1, 0, and 3, 8, 1, negative 1. And you get 2. So then what's the determinant of this guy? It's the product of the diagonal entries, which will give me negative 2. Do you guys appreciate this way of finding the determinant? Do you see how it's a little bit more efficient than doing the cofactor expansion every time? Even though a cofactor expansion, of course, it's going to get you the answer. It's just that here, if you're able to row reduce matrices pretty quickly, which I think at this point you guys should be able to do pretty quickly, then all you have to do is put it into row echelon form, upper triangular. And once you have that and you keep track of the operations that you apply, whether it be a scalar multiple of a row, whether it be adding a scalar multiple to another row, which leaves it unchanged, or swapping the rows, then you can find the determinant by multiplying those diagonal entries that you get at the row echelon form version of the matrix and whatever steps you did previous to getting to that step. Does that make sense? Okay, so I'll give you a few problems here now. And you tell me what you think they are. What is the determinant of this matrix? Negative 2, 8, 1, 4, 3, 2, 5, 1, 1, 10, 6, 5, and 4, negative 6, 4, negative 3. What do you think this matrix is? The determinant of this matrix. It might be a little hard to see this. Swap row 1 with row 3. Yeah. So you can apply the row echelon form thing, right? But I guess you don't see this. Okay. What happens, guys, what happens if I add row 1, row 3, pardon me, doesn't even matter. Row 1 plus row 2 into row 2. What happened?
Get row 3.
Yeah. Yeah. So you get -2, 8, 1, 4. You get when you add it, you get 1, 10, 5. Oh no, sorry, 1, 10, 6, 5. And the next row is 1, 10, 6, 5 as well. 4, -6, 4, -3. What did I just do? I just this looks good. I just added the first row with the second row. That's all I did. In doing so, I get 2 rows that are repeated. They're the same. So you're like, wait, what? Who cares about that? Well, if I were to do one more, like, so first of all, if I apply this elementary row operation, did I affect the determinant in any way? I'm adding a multiple of one row to the next. So no, right? The determinant of this matrix
No,
is identical, right? The determinant of this matrix is identical to this one. It's the same. So what am I going to do here? Watch this. I'm going to do this. A negative row 2 plus row 3 gives me row 3, right? I'm going to just apply this elementary row operation. What happens now? I get -2, 8, 1, 4. I get 1, 10, 6, 5, and I get what? 0, 0, 0,
Zeros.
0. 4, -6, 4, -3. And
Wouldn't
say that again?
I was gonna say, wouldn't that make the determinant automatically 0?
Exactly.
So we didn't really need that intermediate step, right? Because we already had a row that was 1, 10, 6, 5 to add. Am I missing something?
No, you're not missing anything. So, right, you could have not even done any of this. You could have just seen that, hey, wait a minute, if I were to do this, I get 2 rows that are the same row. 2 rows with the same rows. If I apply one more operation like this, I get 1 row of zeros. The determinant of a matrix with 1 row of zeros or any column of zeros is 0, right? Because I apply the cofactor expansion along that row and it all becomes 0. So now what does this tell me? This expands a bit more, right? Again, every single operation that I did here leaves the determinant unfazed, untouched. So this is another property. Note, any matrix that has the same, has at least 2 of the rows or columns proportional to one another proportional to one another has a determinant equal to 0. That's important to see. It's proportional. So in this case, it's proportional because they're the same row. They're the same 2 rows. But if you notice, if I multiply this by 2, right, this becomes 20, this becomes 12, this becomes 10, right? these two rows are proportional to one another. And if I had this kind of matrix, then I would automatically say the determinant is 0, because then I can just do the same thing, right? I can apply operations that make them the same, subtract them, get one row of zeros, and therefore the determinant is 0. So that's important. I'll give you another one. What about this one here? -4, 1, 1, 1, 1. 1, -4, 1, 1, 1. 1, 1, -4, 1, 1. 1, 1, 1, -4, 1. 1, 1, 1, 1, -4. What's the determinant of this very nice matrix here? For cofactor expansion, can we make a row have almost all zeros and then proceed? Yeah. There we go. There we go. That's right. That's right. You can do, you know what? Let me just make something all zeros almost and then apply cofactor expansion. You can do that. And that's how you exploit the properties of determinants and exploit the structure of matrices. So you see how it becomes more computationally interesting. It's not just so systematic. There's also an art to it. There's an art to finding the determinant, for example, of a matrix. And there's underlying structure behind matrices, and there's much more to explore. But the determinants definitely changes the game of things, right? It gives a different light to matrices now. So what would be the determinant of this? Of this 5 by 5 matrix? Anybody have an idea? A whole bunch of ones and a whole bunch of -4s. Does anybody see it? Sometimes it's about seeing it. No? Nobody? Oh, Baldwin, yes.
I don't know if I'm right, but I feel like this could also be 0 because you could start canceling stuff out.
So so it is 0.
Okay.
But what's your reasoning?
Um, I don't know. Sort of in my head, I was like, we could multiply one of the rows by like -4, and then we'll get 0 in one of the pivots.
We multiply by -4. Which one?
I mean, not -4, +4. We could multiply, like, for example, R4 by by 4 and then add it to R5, and then that would get us 0 in one of the pivots.
It does give us 0. But it doesn't. So if I were to do what you said, right? You said multiply R4 with by 4, right? And then add it to. Is that what you-
Yeah,
So you're saying R4, you add it to R5, right?
yeah.
So then what does that give us? -4, 1, 1, 1, 1. 1, -4, 1, 1, 1, 1, 1, -4, 1, 1, 1, 1, 1, -4, 1. This would be what? -4, +4 would be +1. This would be 5, 5, 5 of 16. plus negative 16 plus 1 is negative 15.
Yeah, it wouldn't work out.
No, but that's what you told me.
Yeah.
But yeah. Does anyone else see how we can get to that conclusion that this is a determinant that is 0? But does anybody see why?
I'm taking a shot here and guessing, but would it be if you just eventually multiply by enough scalars, you can manage to get two rows to equal the same thing down the line?
Yeah.
Yeah, I just don't see like an easy way to get to that. It just seems like a lot of process.
Well, what if I do this? What if I do R2 to R1 to R1? Again, you can see this in many ways. What if I do that? So what if I add this to this? What would I get? I would get
So you got,
negative. Uh-huh.
oh, sorry, yeah.
You go ahead.
-3, -3, 2, 2, 2.
2, 2, 2, right? This is 1, -4, 1, 1, 1. And this is 1, 1, -4, 1, 1, 1, 1, 1, -4, 1, 1, 1, 1, 1, -4, right? Now, what if I do the same thing, but use R3 instead? Use R3 plus R1 into R1. What is that going to give me? Do you see? So I take this row and add it to this row here. What do I get? I get 2, 2, right? Then I get what? I get -2, 3, 3, right? This becomes 1, 1, -4, 1, 1, 1, 1, 1, -4, 1, 1, 1, 1, 1, -4, 1, 1, 1, 1, 1, -4.
Wouldn't the first two twos be negative?
They are. See that? It should be. Thank you, Alexa. Thank you, Sam. Sometimes, just adding two numbers, it's impossible, right? And then do the same thing. R4 plus R1 into R1. You might be like, wait, this is getting kind of crazy. This is R4, right? If I add it, what do I get? -1, -1, -1. I get -1 and I get 4, don't I? And guess what happens with the last step?
Turns it into zeros.
Whoa, ski. So this is R5 plus R1 into R1. Pretty cool, right? So there's a structure behind this. This is 0, they're all zeros. They all cancel out eventually. And all I did was apply row operations to each row, right? Row 2 to row 1, row 3 to row 1, row 4 to row 1, row 5 to row 1. Every single operation that I did here leaves the determinant unchanged. So this determinant here is the same as this one, the same as this one, the same as this one. But what happens is I get a row of all zeros and I get everything else 1, 1. 1, -4, 1, 1, 1, 1, 1, -4, 1, 1, 1, -4, 1, 1, 1, -4, right? This is 0.
So is that to say whenever it's in that, I forgot the name of the form, when it's almost just the same on across the diagonal, and every other entry is symmetrical, right? Like almost symmetrical. Then if the sum of all rows is always 0. I might be oversimplifying that.
That's a good question. You can try it yourself. Like, what if you replace these numbers with 2s?
Right, and then like switch the ones out for like 5 or any number.
So the question is, are all symmetric matrices, are all of them equal to zero, determinant equal to zero.
Right, right.
And I would have to say, be careful with that statement.
Okay.
For example, because so this is another thing, right? If you say all symmetric matrices have a determinant equal to zero, based upon this one example of a symmetric matrix having a determinant of zero, you have to be careful because, for example, take the symmetric matrix, which is the identity matrix, that's symmetric. The determinant of that symmetric matrix is not zero. So that statement can't be made. Not all symmetric matrices have a determinant equal to zero. This one does though.
Got it. And the one with ones across the diagonal and all zeros, the identity, that one, is that the only exception, or are you trying to hint at that there's much more?
Well, if the identity matrix is symmetric and it's good, then any multiple of the identity matrix, which will be matrices, right? For example, that have the same that number in the diagonals, right? And then you can complicate that. You can make it like a symmetric matrix doesn't have to have the same diagonals entries. They could have any diagonal entries. So I can make this a 1, 2, 3, 4, 5. It's still symmetric. I'm pretty sure that would not be determinant equal to zero.
Right. So I guess I should clarify then. It's not really any symmetric matrix. It's not a symmetric matrix at all. It's specifically a matrix with the same entries, upper triangular and lower triangular, and then the diagonals all the same value. But again, not the.
And it has something to do. It's something to do. For example, if you look at there's how many ones do you have in each column? There's 4.
The same. So it has to be n by n as well.
Well, you can only talk about determinants with n by n matrices. You can't talk about it with others. And then look at what's in every diagonal.
Same entry.
It's the same entry, but it's something related to these ones, though.
Oh, yes.
Why you cancel out. You understand?
Yeah.
So just because, for example, if this was a negative 10,
it suddenly wouldn't work.
I'm sure it wouldn't be so nice like this. So you see, there's structure behind these kind of matrices that have these properties, and you have to sometimes see it. You have to like play around with it, and then be like, "Oh, wait, there's something about this 4. Why is this 4? And why are there 4 ones? And how does that affect the determinant?" So that's why when I did all of these steps in successive fashion, I got a whole bunch of zeros because I saw this, because it's just by seeing, oh, look, if I add this to this, to this, to this, and to that, when I apply this to every single row, the result is the same. But it's because they add up the 4 ones, they cancel out with the negative 4s after all of that.
Got it. Okay, thank you, Professor.
Yeah. So that's pretty cool, right? That we can so this is a moment in time where you see how everything that you've learned in the beginning kind of becomes more meaningful now that we're talking about determinants. The whole elementary row operation comes back. The elementary row operation has an elementary matrix, which comes back here. Each elementary matrix has a determinant, and there's only 3 kinds of elementary matrices. So there's 3 kinds of possibilities. You can either multiply by the scalar that you're multiplying by, you can either multiply by -1, or you can do nothing to the matrix. Now, all of this is now headed towards something that's extremely important for why determinants even matter so much. So now we're going to head into a place where we understand why determinants are even like meaningful to begin with, beyond just computing something with the rows and the columns and getting a number every time. You have to remember about invertibility. And invertibility of matrices is directly connected to its determinant. So we have, again, invertible matrices, right? Which are called non-singular matrices. Versus non-invertible, which are called singular matrices. So again, very simple, right? Invertible matrices, the inverse exists. Non-invertible matrices, singular, and inverse doesn't exist. Now, how is that related? How are these two separate categories of matrices? How are they related with determinants? Which one is which? So which one do you think has non-zero entry, a non-zero determinant versus a zero determinant? So yes, Baldwin.
So the non-singular matrices have a non-zero determinant.
The non-singular matrices have non-zero determinant. Yes. How come?
I watched the video on YouTube. And that's what
Nice. Who did you see it from? Which
I forgot the channel, but they were just going over the differences between
one blue,
non-singular.
three brown, was it three blue, one brown guy?
I think it was him, yeah.
Yeah, he's the go-to for that. But do you remember why this is true? So this is true. Non-invertible matrices, determinant of A is 0. Invertible matrices, determinant of A is non-zero. Can anyone give me a good reason why? Beyond just watching a YouTube video and saying, hey, that's what they said.
Because I have to divide by 0 to get I have to divide by the determinant to get the inverse, and I can't divide by 0.
That's a good reason, but how do you know you have to divide by the determinant? Mir. So that whole divide by determinant, that's true for what? That's true for 2 by 2 matrices, right? But when you find the inverse for 3 by 3 matrices, did we ever speak about the formula for 3 by 3, the inverse of a 3 by 3 matrix? We never had to divide by the determinant, right? For a 3 by 3, finding the inverse of a 3 by 3 matrix. So yeah, that's a good reason for 2 by 2 matrices. But then how do you apply that to a 3 by 3 matrix, or a 4 by 4 matrix, or a 5 by 5, or a 10 by 10, or a 100 by 100 matrix? How do you know that that also applies to them? So what I'm trying to get you guys to think about is what does it mean to be invertible? Remember, there's those equivalent statements. So when you're invertible, when your matrix is invertible, an inverse exists. So there's another matrix out there that when you multiply those two matrices, it gives you the identity. That's one way of explaining invertibility. What's another equivalent statement for invertibility? If you guys remember.
If I multiplied it by the inverse, I would get the identity matrix.
Correct. Yeah, I just said that. What's another one? And it has to do with row reduced echelon form. What's the row reduced echelon form of an invertible matrix? You guys remember that? If you have an invertible matrix, any invertible matrix, and you find a row reduced echelon form for any invertible matrix, what do you get?
The identity.
Identity. What happens when you do that for non-invertible matrices? What's the row reduced echelon form of a non-invertible matrix? What happens every time for a non-invertible matrix, a singular matrix, when you find the row reduced echelon form of that matrix? What do you get? You get at least one row of zeros, right? Don't you get that? So you get a matrix with at least one row of zeros. So that is why the determinant of a non-invertible matrix is A. Because if I were to write this in a row reduced echelon form, right, determinant, if I apply E1, E2, whatever, EK, right? If I apply these elementary row operations to A, eventually what happens? I get a determinant with row full of zeros. So this would give me a 0. But what happens when I do it to A? I always get elementary row operations, right? I'm able to, so the row reduced echelon form of an invertible matrix is the same thing as if I were to apply EK, right? EK minus 1 all the way to E1 times A. I get the identity. If I take the determinant on both sides here, it's always non-zero. Do you understand? I always get non-zero determinants for each of these matrices because what I equals 1. The determinant of identity is 1. So that's the reason why. And this is a very important. If you have the determinant of a matrix being 0, it's non-invertible. So immediately, what do you know? This matrix, there's no inverse to this. This matrix, there's no inverse for this because the determinant is 0. This one does though because the determinant is non-zero. So now that's an additional equivalent statement that we have. Okay. So a matrix, a square matrix is invertible if and only if determinant of A doesn't equal 0. Conversely, if a square matrix is non-invertible if and only if determinant of A does equal 0. Okay. Is that clear? Okay, guys. Make sense?
Yes.
Awesome. So let's do a few more things with determinants. A few more examples here. Let's see if we have a determinant. So if A is a 3x3 matrix, and determinant of A equals 7, find determinant of 3A, determinant of 2 times A inverse, determinant of 2A inverse. Yeah, it's almost it's almost adjoint time. Yes. So let's do this real quick though. So if you have the determinant from the previous properties that we have, right? If the determinant of 3a, what would be the determinant of a matrix, the matrix 3a, if the determinant of a is 3, is 7?
27 times 7.
Right. It'll be 3 cubed times 7, which is 27 times 7. Somebody out there in the street? 189. Okay, thanks. And then next, what's 2 times a inverse?
8/7.
Right, right. It will be 2 cubed multiplied by the determinant of a inverse. But we know the determinant of a inverse is 2 cubed multiplied by 1 over the determinant of a by the formula, right? And so this becomes 8/7. That's right. See? Not bad, right? And then the last one,
1/28.
1/28, because this is really what? 1 over the determinant of 2a. This is 1 over 8 times the determinant of a, which is 1 over 8 times 7.
Oh, screwed
Right?
up the math there.
Because it's a 2. It's a 2. And this becomes 1 over 56. Okay, so now I hope you feel more comfortable now with determinants and their properties. And there's, yeah, so we're good with that for now. Now there's another way to find the inverse of a matrix using what's called the adjoint matrix. And it's not so crazy, right? It's not such a crazy thing, as long as you know what cofactors are. So the matrix of cofactors looks like the following. It's a matrix where every entry is the cofactor of the original matrix. So we already know what cofactors are, right? So this would be C11, C12, all the way to C1 N. So we C21 all the way to CN1. This would be CNN. And remember what C1, what C sub ij? Remember what this was? You guys remember what the cofactor was? Anybody? What's the cofactor of a matrix of the entry ij? You guys remember this? This is -1 to the I plus j multiplied by the minor ij. And remember what the minor was? It was the determinant. So don't forget this, guys. This is the determinant of the submatrix. So it's a smaller matrix that has row I and column J of original matrix excluded. So what we're doing is we're creating a matrix where every entry is this, the cofactors. So all the cofactors. Normally, when we do the cofactor expansion, we only go along one row or one column. In this case, we do all the cofactors at once. We do all of them. So we take the submatrix for every single entry and multiply by -1 to that power. And that would give us the cofactor matrix. Now, what's the adjoint matrix? And they use this they use like the abbreviation ADJ of A. What's the adjoint matrix? It's just the matrix of the cofactors, the transpose of that. That's all it is. So this would look like this now. This would look like C11, C21, all the way to CN1. This is C12 all the way to C1N. This is CNN. So the transpose of the cofactor matrix is the adjoint matrix. So yeah, I know. Tasif is like, oh man, this must be like some crazy, like otherworldly, like matrix representation that No, that's literally what it is. Very, very anticlimactic, isn't it? Like this is the more important one. This is the more interesting one than this. This is just the transpose of this. So you should understand this first, and literally just take the transpose of that. Yeah, it's the matrix of cofactors is the real thing. I don't know why they use the word adjoint and why it makes it seem like it's so much, like they could just use the transpose of cofactors. That's it. But anyways, regardless, how do we use this now? Well, we can find the inverse of a matrix, and this is where Mir comes into play when he talks about determinant. It's actually 1 over the determinant of A multiplied by A times its adjoint. Let me see if I got that correct. The determinant. Pardon me, there's no A here. Yeah, it's just this. The adjoint of A. Yeah, so that's all it is. Now, there's a reason why this is true, and I can get into that. It's a bit more a longer statement, longer proof for why this would be indeed the determinant. But we'll see this first as an example. So what is A inverse again? You have to find the determinant of A first. So what's the determinant of this matrix here? 0, -4, -3, -3, -1, -4, -2, 1, 2. So what do you want to do here? Do you want to do the row echelon thing where we have the upper triangular? Do you want to do the trick for this? The trick. Okay, so let's do the trick. So this is going to be 0, -4, -3, -3, -1, -4, right? So we have this diagonal, and this diagonal. So when you do that, you get -6, you get 0, you get 12 times 2 is 24, right? That's what you get for these. And then you get this diagonal here, this diagonal here, and this diagonal here. So this becomes 0. This becomes negative positive, right? Positive 9. And you get a negative 16 times -2. So this is negative 32. You add these up, and you subtract them. So this will be positive 18. And this would be negative 23. And so the determinant of A is going to be negative 23 minus 18. And so you get what? Negative 41 as your determinant. And you can check that on your own with the calculator if need be, just to make sure everything was done correctly. And so let me just check that real quick. You can edit it, right? On your calculator really quick. So 0, -3, -2, -4, -1, 1, -3, -4, 2. And then you take the determinant. You get -41. So once you have that established, then you have to find the adjoint, which again means you have to find the cofactor matrix. So what's the cofactor matrix? It's C11, C12, C13, C21, C22, C23, C31, C32, C33. So the nice thing is here is that the cofactor is just, so C11, right? What's C11? It's this determinant here, which would be what? It would be -2 minus -4, which would be -2 plus 4, which would be 2. And because I am in the first entry being 1, 1, this would be positive, right? So this should be a 2. What's C12? We'll cross this out, cross this out. You get -4. This would be -8 plus 3, which is -5, but I have a negative associated with that. So this would be +5, right? Does everybody follow what I'm doing? C 1, 2 will be +5. What's C? I should write it like this. C12 is 5. What's C13? This will be positive. 16 minus 3 is 13. And then C21 would be what? C21 is going to be -3, 2, and this will be -4, -2, right? So this will be -6 minus +8, right? So it'll be +8, and this will be -14. But C21, this is -1 to the third power. So this will be, let me just see that again. So -3, sorry, -6 minus 8. So it's -14. It's -14, this will be +14. This is +14. As you can see, it's not like the most, it's not the most interesting way to find the inverse. This becomes 0, this becomes, it's a times, yeah, it's -6. So this is -1, 2 plus 2, this is -6, right? So this would be -6. And then C23. But then think about it. Think about trying to do this. Think of, well, actually, The thing is, like, if you were to use the inversion algorithm here, it's also a time sink. This was actually a bit better, because in your attempt to make this into row reduced echelon form into the identity, yeah, it is a lesser of two evils, yes. These numbers are going to be, you've seen it, right? When you have these fractions that pop out of nowhere. And look at this fraction here, -41. That's crazy. Because the idea is you're going to take this cofactor matrix, you're going to transpose it, and then you're going to multiply that by -41. Imagine trying to come up with that utilizing the inversion algorithm. It's not going to be pretty either. So this is actually much better, even though it seems kind of like not that interesting. This is negative, right? C23. So we exclude this. This becomes 0. This becomes +9, but it's -9. So it's negative of a -9. You have to be very careful with the negatives. This would be +9. And then again, C31. What's C31? This would be positive because 3 plus 1 is 4. So C31 here, I got -3, I got minus a +2. So -3 minus 2 is -5. So this is -5. This is C32. This will be negative. This will be a negative. C32. You get 0. The nice thing about the zeros is it just gets rid of that number real quick. You get -8. So -8 is +8. So this is +8. And then the last one, C33. Get rid of this. This here becomes here. This becomes -12. Positive. So this is -12. This is -12. Great. Wow. Okay. And so what's the adjoint of the matrix A? It's just a transpose of the cofactor matrix. So this would be 2, 14, -5. This would be 5, -6, 8. And this would be 13, 9, -12. And then what would be the inverse? It would be 1 over the determinant of A multiplied by the adjoint of A. So this would be everything divided by 1 over -41. So this would be 2 over -41. This would be 14 over -41. This would be -5 over -41, which is positive 5 over 41. This would be 5 over -41. This is positive 6 over 41. This is 8 -41. This is -13 over 41. This is -9 over 41. And this will be finally positive 12 over 41. Woo! Okay.
Would you want us to do that last step on the exam? Like break it all down instead of just leaving the scalar on the outside of the matrix?
That's fine too. That's fine too. Leaving it out there is fine. That would be the same thing. But for this, I just like sometimes having the matrix. Yeah, usually I put the negatives in front. Having that scalar just inside. But again, it's the same. It's the same thing. And just to make sure we aren't crazy, let's actually compute it. Just to make sure. So here we have. So we got the second matrix. This is a 3 by 3, which is not bad to plug in. So here we go. So we have 3 by 3. Then we have 0. We got -3, -2, -4, -1, 1, -3, -4, and finally 2. So we have our A matrix. We go out of here. We go to second matrix. We select our matrix that we found, A. Put the negative on top. Enter. We get this craziness, right? And then we do math. Enter, enter. And guess what we got, guys? Did we get the same thing? We got a whole bunch of negatives there, right? You see that? Beautiful. Beautiful. Excellent. So imagine trying to do in the inversion algorithm with this. That would be crazy. It would be. Because you have all these fractions and they're going to come up with over 41. Good luck with that. So actually finding the cofactor, even though it is a little bit like time consuming, it's actually a lot easier, a lot cleaner in getting those numbers because you can find a determinant and now you have very sophisticated ways to find determinants of matrices, finding the cofactors, also finding more determinants, but you know, it actually works out pretty nicely. Does that make sense, guys? Everyone good with this? Finding the inverse of a matrix, utilizing the adjoint, and the adjoint being the cofactor, the transpose of the cofactor matrix, and applying this. So good. Good. We have a new way of finding the inverse. Excellent. Cool. Determinants are very useful, very helpful. And now, there we go. Okay. So we talked about the adjoint, we talked about invertibility, we talked about determinants, we talked about how the row operations affect it, and so on. And one last thing about determinants. And then I'm going to go over certain things about the actual homework. So what's cool also about determinants is beyond the fact that you're able to compute it and it tells you the invertibility or non-invertibility of a matrix, there's actually geometric interpretations of this stuff. So let's suppose I have a vector in 2D space, pardon me, in 2D space. So we have 1, 2, 3, 4, 4, 3. So make believe I have a vector. So we haven't really gone so much into vector. We talked about vectors a lot. We mentioned them, but I haven't gone so deep into like this whole vector stuff, geometry of it yet. But this is a vector. I'm gonna call it V. So V is 4, 3. Okay. Okay. And another thing, I noticed on the homework there's different ways that they note the different notation for things, right? So there's various ways to represent a vector, right? We talked about the row vector, so we can write this literally like this: 4, 3. That's the row vector version, right? You can also write this as a column vector, which would be what? Looks like this, right? 4, 3. Almost looks like a binomial coefficient. So just to like make sure it's not, sometimes we use a bracket here. This would be the column vector. And I'm just saying we normally use column vectors for vectors. We normally use that. And then there's like this other notation people use sometimes, which is like this triangular, like this lower than, or greater than, lesser than, greater than symbols. They're the same thing. Okay, guys. So when you see this, it's just another notation. And usually they use this to distinguish between a coordinate. So normally people use this and they think of coordinates. And then when they see this, they think of a vector to that coordinate. Okay. So that notation is not much of a difference. So either way you see this, it's the same thing. It's this vector here. So this is V. Okay. Just want to make that clear. And then this is going to be another vector 1. This is 3. This is 6. Let's look at this vector here. Actually, I'm going to use a different color for this. Right? So we have a vector here, 6, 1, 1, 6. So I'm going to call this U. This vector U, I'm going to call it 1, 6, right? Now, what's cool about vectors is that when you add these vectors up, there's something called the parallelogram rule, which means that I literally take this guy here. I'm literally just going to copy this and paste it on top of the tail here. So this would be my coordinate here. This would be V. That's one thing about vectors. You can associate, you can move them around as long as the length of the vector stays the same and the direction stays the same. I can move them around. Same thing happens here. This guy. When you do this, right, when you have parallel lines, 2 pairs of parallel lines, you create a parallelogram. Now, you can actually find the area spanned by, you can find the area spanned by these two vectors here in creating a parallelogram. And it's given by this formula. So the area of a parallelogram is given by, what's that formula? X1, right? It's X1, Y1, 1, X2, Y2, 1, X3, Y3, 1. And if you notice, so what are these X1s, X2s, and X3s? Well, what are these coordinates? These are the coordinates represented by the triangle that can be formed. So this is going to be my, so X1, X2. So X1, Y1, X2, Y2, X3, Y3 are the coordinates of the triangle formed, that can be formed in the parallelogram. So what are the vectors here? What are the coordinates here? Again, we already discussed that, right? This here is 4, 3. This here is 1, 6. And this here is 0, 0. So we're taking the determinant of what matrix, we're taking the determinant of this, 0, 0, 1. If I call this X1, Y1, X1, Y1, I call this X2, Y2, so this is 4, 3, 1. And I call this 1, 6, 1. Is it 4, 6, 1? Pardon me, this should be 7. Sorry about that. This should be 7. It doesn't really matter. It's just, it matters for the computation aspect of it. So this should be raised up a bit more. This should be up here actually. And this U should be a little bit, it's just based upon the computation that I want it to be. So this should be, sorry, this should be, okay, not helping me out here. Yep, doesn't work. Okay, so I'm going to write it like this. Hold on. All right, so this is 7. This is 1, 7. So this will be 1, 7. Okay, and then this here would also be the vector here. So this is U. So this area here can be found by taking the determinant in this form where each of these coordinates are the coordinates of the triangle that's formed within the parallelogram. And so when we find this, how do we find the determinant of this? We can do the trick. We can do the cofactor expansion thing. The trick actually takes a little bit longer, I would say, because the cofactor, because you have a row with nearly all zeros. So just use this row. And then this will be the only entry that appears. This is the entry here is 1, 3. So if I want to do the cofactor expansion for this, C13, right? This here would be a positive number that appears for the C13. So this actually is just going to be the determinant of 4, 1, 3, 7. And when you multiply this, this becomes what? 28 minus 3, which is 25. Does everybody see that? Why would it be negative? Why would it be negative 25? The negative 1i plus j, right? The ij here is 1 plus 3, it's 4. So negative 1 to the 4th power would be positive. And if you notice, this is a parallelogram. And what's the area of a parallelogram? Base times height, right? So if you were to find the base of this and the height of this, the base of this would be 5, if you notice here. This is a 4 by 3 right triangle. This is a this hypotenuse would be 5. And then if you were to extend this a bit more, if you were to extend this and then draw a line here, you would also find out that the height here would be 5. That's something that you can try on your own. And the area would be 5 times 5, which is 25. And now, what would be the area of the triangle? What would be this area here? By the symmetry, right? It's going to be half the area of the, yes?
Yeah, 12.5.
Right. So what's the formula for that? The formula would be 1/2 x1, y1, 1, x2, y2, 1, x3, y3, 1, which will be a half of 25, which is 12.5. And then the determinant, right? We're using determinants for this. And then the determinants can be applied also to three-dimensional space when you have 3 vectors and you want to figure out the area spanned by those 3 vectors, or the parallelepiped, which is like the 3D version of a parallelogram. And you've probably seen that before in your Calc 3 or multivariable calculus. So see, determinants become more than just a number. They become actually a geometric description of areas, which is pretty cool. All right, guys. So that's all for today in terms of determinant.